right, so here's what I want to do, and tell me if you can see okay. I'm going to zoom in a little bit. But I just wanted you to check 1.2D before we say, you know what, difference quotient is good to go. Can you see that? Okay, I will take your silence to mean yes. But if you're having trouble seeing that, just let me know. Take out 1.2D, and let's take a look. And just make sure you did okay. Fix any mistakes you have, ask any questions that you need to, but then we'll keep going. So there's number one. Okay, so two different spots for the x, so the x plus h goes in twice. Expand it out and see how you do. I'll even share my screen on here. So if that version works better for you, you can pick whichever screen you'd like. So maybe that helps. I'm going to scroll, if that's okay, if you're ready. Just unmute yourself and stop me if anything happens that you need to see again. But I just wanted to throw one more at you that had a coefficient in front of the x, and I put a negative there too, so that we had to deal with that. But remember, whenever you expand stuff out that has power attached to it, just make sure you take care of that power first. All right, x plus h squared first, then multiply everything by -3. Then we can combine some like terms, factor out that h, and just watch your signs. That's something we want to be really, really careful with going forward. All right, so that's why I like to do this, right? I put the minus and then I put everything in parentheses. But maybe you're good and you want to just say, yeah, I can do plus 3x squared plus 2. I can do that. I'm okay with that as well. Okay, so that's 1 and 2. Moving on, stop me if you need to. Here comes 3. Get rid of all that. What I hoped would be worthwhile is to just drop Pascal's triangle up there for 3 and for 4, especially for 4 when we got to the x to the 5th. There you go. Take a look. Tell me what you think. And really, if you get the right answer, there's probably a pretty good shot you did it well. It's tough to fall into the right answer the wrong way. So if you're just going right down to the end and making sure that what you have boxed in is what I have boxed in, you're probably good. Okay. Without further ado, the big one, x to the 5th plus 4. Right, coefficients are Pascal's triangle, the row that starts with that same exponent with the 5, and then 5, 0, 4, 1, 3, 2, 2, 3, 1, 4, 0, 5. Just kind of worked my way across that way. If you want to do that side work like we had done when we first started messing around with it, you can just kind of come over onto the side of your page or on a separate piece of paper or something like that and do whatever side work you need. So that as I work through a problem, right, I'm just equals, 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 just kind of working my way down, so that I'm not stopping in the middle of the problem and doing some kind of separate work somewhere within the same space. I want to do that separate work. Literally, like I'll put a line down the edge of my paper and I'll do some work over here so that you can see those two columns. Good? Questions? Unmute yourself. Give me a shout. I'm looking at the chat too, so if anything comes up, I will check that out. But if you're good and you're ready, let's jump back into 1.3. Okay, we're here until 9:55, so we've got about 40 minutes. I want to make sure that what we talked about last class, whether that was Wednesday or Thursday for you, that it's still in there somewhere. You still remember how to do that. So I'm going to jump into the textbook. Now, I'm going to have the textbook up here, and I'm sharing my screen over there. But if you wanted to open up Chapter 1 and go to Section 1.3, you could do that. I'm going to be picking problems out of there for us to look at and make sure we're okay with. So That's always found in Canvas on Pages, so you can go right to there. And I hope you just kind of download your PDF and you just leave it there so you don't have to worry about going back to it. So let's do that. Let's go to the textbook. And what I want to do, I'm going to change some of the directions here. I want to look at section 1.3 in the homework itself. I want to look at 25 and 26. All right, I want to do these two, and we'll do them separately, but you can start them both if you want to. And I want to kind of touch on all of the ideas that we were looking at last class, where we decide, and so this is for both 25 and for 26. I know you can't see that on my shared screen, but if you're looking at the camera, you can see what I'm circling. I want to know, where is it increasing? Where is it decreasing? Where is it constant? Right? There are your intervals. And then let's list all of our global and all of our relative, maybe you remember the word, all of our external. Okay. And I want you to try it first. I think we did enough in class. I think you have the right idea, right? These are going to be your domain intervals, your open domain intervals. Okay? And then these are just points, right? Those highest and lowest points, both kind of overall and then relative to the space nearby. Now, because it's not always clear in the textbook whether the graph keeps going or not, I don't know why they don't do this, but there should be arrows telling you that this graph continues on past the edge of the screen. Okay? That'll give you a better chance to figure that out. So take a minute or two, try it out, see how you do. I'm going to jump into the whiteboard feature on my projector to actually work through the problems here in a minute. So try those out. Sit there and piece of paper in front of you, something to write with, something to write on. Try 25, increasing, decreasing, constant. Global max, global min, relative max, relative min. 26. And the functions are written there too, so there's no confusion, right? And you can graph them yourself too if you wanted to check these out, because these graphs are pretty pixelated and rough. The textbook's kind of capturing of the calculator screen is old, right? So you want to be able to pull those up on your own graphing calculator, or just go to Desmos or something like that online to check that out. But you will want to have your calculator with you today for one thing I'm going to talk about. So if you have that nearby, keep it in there. So let's call it 9:20-ish. Just take like 2 minutes, and then I'll start working. Okay? And unmute yourself if you have a question. Gonna peek at the attendance, see who's here. Connor. Another minute or so. And you can assume that these points kind of fall in nice lattice points. right? Like that one is perfectly exactly where you think it is. And so these numbers on the outside tell you the edge, right? So there's 6 boxes that way, 6 boxes this way, 4 boxes this way, 4 boxes that way. Okay, try your best to put some finishing touches on stuff. And if you're done, good. I'll get started here in just a moment. I want to give everybody a chance to try this out. And we'll do 25 first. Let me see. Maybe I should. Sure. That'll help. All right, I think you're ready, hopefully. I just want to give myself a space to try this out where I can kind of write behind, okay? Okay. So if we wanted to talk about this one and where it was increasing, and we know we have these arrows on them kind of going forever, right? It's going to be increasing all the way, and I know it goes down forever this way, but because it's a function, it's going to go out forever as well. It's increasing from negative infinity all the way to whatever that x value is right there, which is 0. Okay. And then it stops and takes a turn and starts to come back down. So that'll be decreasing. But then right here, it takes a turn and starts to head back up again. And so it looks like that's going to happen from 2 and then onward forever from there. Okay. Open intervals always, right? Exclusive intervals, but we don't want to include those endpoints. And because they're sets, we're going to put a u between them. Okay. Good. Okay, let's switch it up. We'll go decreasing in red. Looking for an interval where this graph is going down from left to right, and that's between 0 and 2. And then constant, none, or non-applicable, or nowhere, or whatever you want to say. Good with that one? Sweet, awesome. Okay, let's try the next one. And this, again, this is being recorded, so you can always go back and take a look. So I'm just gonna keep rolling here. Let's go back here, you up, right on top. Move this out. Okay, this one's a little different. There's a reason why I wanted to talk about this one. Because it can be really tough to see exactly what's happening when you look at a graph from the textbook. Right? Now, I had to put those arrows on there, and that's kind of up to you to realize as well. If it hits the edge of a screen, whether left and right or top and bottom, or some combination of those, it's probably going to keep going. But we have this to help as well, and we're going to need that to make some good sense out of all this, okay? So increasing going up from left to right. Looks like every box is worth 1 in every direction here. So looks like it starts at 1, and it's just going to keep going up. And that's the only place where that's happening. Okay. So hopefully that went well. Decreasing. I know I switched up the color scheme on you. Looks like it's going to be happening from negative infinity all the way to negative 1. But as soon as it gets to that negative 1, right, you can see me standing on the chair. I'm not going down anymore. I'm not going up anymore. I'm just there. I've made it to the bottom. But the real question, I think, that is kind of tricky to tell when you look at this graph is what's happening in between, like from here to here, in this space in between. Because it's not on like a color calculator where the color of the graph and the color of the axes are different. That's why I love the TI-84 color edition, because when you graph stuff in there, you can tell whether or not things are being plotted on your axis. I know where I'm crossing the x-axis, where I'm crossing the y-axis, because the color makes a really big difference. And so what you might have seen, which can be tough with this, is that it might seem like in here, between -1 and 1, that it's constant, that it's connected from this point to this point. Okay, let's take a look at what's in here. X squared minus 1 is what's underneath that radical. Okay, and that's what gave us this graph. But the question is, what's happening right down there? Are we just cutting through the x-axis or not? Well, think about the numbers between -1 and +1. Right? Because that's kind of the interval that we're looking at here. That's the only thing that wasn't included. We stopped at -1 and we kind of picked it up at 1. What's happening in between? Well, let's pick a nice number like 0. What would happen if we went into here? Let me erase this. What would happen if we went back into here and you dropped in right there if you dropped in 0? Think about what would happen underneath that radical if you changed x squared minus 1 and you dropped in the 0 for x. Now, if you don't see me writing on here because you're looking at my presenting screen, just pin this video instead. Drop in 0, 0 squared, 0. 0 minus 1, -1. Can we take the square root of something negative and get a y value back that we can plot? So there's actually a gap between -1 and 1 where this graph doesn't exist. And that could be really hard to see when you look at it on something like that. But if I were to go in and say, like, open up a calculator to take a look at this, because not only did they give me the graph in the textbook, but they're also going to give me the function that goes with it, it might be a whole bunch easier for me to see what's actually happening if I take a look at my own version of this graph, right? If I go in and I say, all right, I'm going to go to y equals, I'm going to get rid of that piecewise stuff that we looked at, and I'm going to type in the square root of x squared minus 1, and when I graph, right, I see that gap in between -1 and 1. But something else happens in the calculator that could drive you a little bit crazy. As you get closer and closer and closer to that x-axis, you see that there's this visual space between the x-axis and, let's say, where the graph is actually coming down to. And like, does it actually make it all the way down there? Does it actually make it all the way down there? It might be hard to tell unless you start to zoom in. Okay, now we're a whole bunch closer, right? This is just 1 right here, so maybe that's like, I don't know, like 1/5. And so I'm getting closer and closer. Okay, let me zoom in again and see what happens. Okay, like there's -1 right here, and I can see the graph is starting to come down right there, and the graph is starting to come down right there at 1. That's really hard to tell, and the reason there's that gap on your calculator that doesn't actually exist, because I can go all the way to -1 and I'll just get 0. So it should be, let me zoom back out one level so you can see. It should have come all the way down right here. Like this red part of this graph should be here. There should be a point right there and a point right there, because if I have x squared minus 1, sure, I could drop in 1 or -1 and get 0 underneath, because square root of 0 is 0. But when the calculator gets so close to a point that it has to come down almost vertically, the graph of a function is the only thing that this thing can handle. But a vertical line is not a function. And although this whole graph isn't vertical, there's a section of this graph, this very, really small little section, where this is so close to being vertical that it's less than a pixel wide on your calculator. Because that pixel is trying to be drawn, but it can't draw a vertical line, it has to stop. So the calculator is imperfect too. The textbook, not great. The calculator, not great, but put these two together, put them side by side, and that gives you a much better idea of what you're looking at. So I just wanted to show that to you, right? Calculator's gonna do stuff that's not necessarily true. But we have both, right? We have the textbook and we have the calculator. All right, so if we look back at this picture, let's do it this way. So increasing, decreasing, when we talk about constant, you might have put from -1 to 1, but it's not actually there. Okay, there is no constant interval for this function because this isn't actually being connected. But you can see, like, this graph does a much better job of coming all the way down, stopping there. Okay, Good? Okay, so that's the old stuff from last time. Any questions otherwise from last time? Increasing, decreasing, constant, relative min, relative max. Oh, we didn't talk about those. Oh, I didn't do those. Let's back up. Let's do 25. Sorry. Let's do that. Let's go 25 first. Let's do relative min, relative max. Okay. Well, we'll do global ones first. So let's say, okay, here are going to be my globals. And I don't know, I'll do it like this. Min, max. You can design a table if you wanted to. Like, okay, here are going to be my global ones. Here are going to be my relative ones. However you decide to tell me how it all works, whatever, works for you. I'm okay. Do we have a place on this graph that is the highest point that is higher than all the other ones? Nope. And that's okay. Oh, that's max, sorry. But same thing for min, right? Same thing over here. There's no point on this graph that's going to be lower than all the points. And so we don't have a global or an absolute maximum or a minimum, but we do have a couple spots on here that are worth looking at where in the space nearby, right, kind of relative to the points around it, it is the highest point on that graph. And there it is right there, right? We've got this max there and this min right there. So a relative minimum at 2, 0 and a relative maximum at 0, 2. Negative 2, sorry. Negative 0, negative. What am I doing? No, 2, negative 2. I'm on it. I got it. You're all looking at me like, what is he talking about? I knew there was a negative in there somewhere. It's definitely not right there, though. All right, there we go. 2, negative 2 is your min. 0, 2 is your max. Not bad. Good. Okay. Oh, next one. Next one. Because I want to get to some newer stuff today. Let's get rid of, well, not everything. Let's get rid of that, and that, and that. Going up. All right. Do we have a point on this graph that is higher than all the other ones? Nope. So same thing here. We have no global max. Do we have a point that is a global minimum? That is the one and only lowest point on this graph. I don't think so either, because these two exist at the exact same y value. Now, let me get back to you to be sure, but I really would honestly say that there can only be one. Kind of like Highlander, there can be only one. And if there are two that exist at the same exact y value, I can't really list them as the global maxima. It's global, there should only really be just the one. Relative, for sure. All right, we can say, yep, negative 1, 0, and 1, 0 would be your relative minimum. I think that's okay. So I'm not going to be super picky about it. I just want you to be able to see it. Right? This is all in preparation for calculus. Always has been, always will be, and definitely no relative max, because it just keeps going up. All right, we never take that turn. We're looking for that hill or that valley. We're looking for relative means and max. Good. I see like 8 of you, and when I say that, normally you like shake your head up and down, so that makes me feel better. Those of you that have your camera on, so thank you. I get if you don't want to turn your camera on, but for those of you that have it up, thank you, so I can get some reactions. Done. Okay, we're good, right? Increasing, decreasing, constant, relative min, relative max. Boom, done. Moving on. Okay, last thing in this chapter. Okay, so I'm going to go back to the textbook for a second. Let me get rid of all this. I'm going to zoom back out so I can find where I want to start. I'm not going to be in that homework section just yet because we haven't practiced it yet. But I think it's something you've seen before. Most of us, if not all of us, have, let's go back. Let's work our way backwards. Let's make sure we did it all. I'm actually going to do that. Let's go all the way back and make sure we're feeling good. Okay, 1.3 graphs of functions. Sorry if this is fast, but domain and range. Cool, and some practice. Great, domain and range, up and down, left and right. Vertical line test, done, cool, we know how to do that. All right, increasing, decreasing, constant. If you want the super technical version of anything, you're looking for boxes that look like that. So if you are like moving towards a degree in mathematics, like if you want to really study math, then you want to be able to say certain things mathematically. So dive a little deeper into the notation and the words that they use. But I want this class to be accessible to everybody, depending on what direction you go. Okay, increasing, decreasing, constant practice. All right, relative minimum and maximum values, which we're calling minima and maxima, and some practice. All right, let me do this one first. What if we have a function that it doesn't land on a really nice point and you don't want to guess your way to whatever that spot is? Like, let's pick this one here in example 6. Negative x cubed plus x. Let me take out my calculator. Negative x cubed plus x. So you have a calculator sitting in front of you. This is the kind of thing that I was talking about. Do the same thing. Join me, okay? Go to y equals, type it in. Or decimals is fine, but you need to be able to click these buttons on the calculator. So I wanted to walk you through the algorithm on how to get there. And maybe you've seen it before. But if I took a look at this graph, and I know I've said this to some classes, but not all of them, so I'm going to repeat it. All these buttons up here at the top are for graphing, and the one in the middle, that zoom option, is a great way to get you started on seeing what you've got. But how do you pick a window that works well for you? You can pick one of these options. Something like graphing sine or cosine, yeah, like zoom trig, number 7 would be a good one. And a square window is really what I'm hoping for. I want my boxes to be squares, not rectangles. On the graph paper, that's kind of sitting behind there. So pressing zoom 5, it's a little close to start at zoom 5 because it's going to take you -4 to 4 and then like -2 in a little bit down to +2 in a little bit. But this distance and this distance are equal. So that's kind of nice. If you feel like you're too close, maybe you can't see the whole function, you can start in zoom standard, zoom 6. That'll back you out a little further, and then you can square it out by pressing zoom 5, and it actually pulls you out and gives you a better version of that graph. Because there are going to be lots of hidden things not necessarily happening near the origin, right? The space that they gave us was -4 to 4. Like they gave us kind of this window. Right? That's what zoom square is going to do from the beginning. It's going to give you a window that kind of looks like that, which should be the same shape as your calculator. But sometimes, like maybe we want our own window. Maybe I want to back up, take a look at the function, but maybe I want to look like down here for some reason. Or maybe I just want to look at some tiny, tiny, tiny little place right there. And one of the things that I wanted to show you today, before we even say, all right, how do I find that point right there and how do I find that point right there? Because there's a way to do that. The calculator can give us the best approximation if it's not pretty. I want to show you how to zoom to a certain space without having to change your window and pressing all of those buttons. Okay, because window will tell you, okay, what is how far to the left and how far to the right? How far down, and how far up do you want me to go? Right? And how often do I want my tick marks? How often do I want tick marks on my graph? Okay. These two are what happens when you just press the left and right arrow keys when you're in the graph itself. Your delta x and then your trace step. Okay. But we could play around and I could say, okay, I want my x's to go from -10 to 10, or maybe I want them from -2 to 7, or 3 to 6, or whatever it might be. You can mess with any of these numbers by pressing on window, but it can be a little tedious in that process. I wanted to show you something really fun that I really, really like to do when I'm graphing. When I know that I want to zoom in to, let's say, the space where all the action's happening, right? Kind of right in there near the origin. Now, you could, of course, just press zoom in, right? You can say zoom number 2. And you see that nothing's changed. It's just still sitting there, but the cursor is now blinking. It's waiting for you to pick a center to zoom. Like when you pinch and zoom on your phone, you don't always zoom into the middle, right? Maybe you zoom to the top corner and it's going to pinch and zoom there. That's what this is doing. And you can just press your left arrow or your right arrow or your up and down, and it will move you around the space and pick a center for you to zoom, okay? And that's nice. So you can pick wherever you want to zoom in. And it's going to always zoom you in 4 times. You're going to get 4 times closer. And then you press it again, you're going to get 4 times closer and then 4 times closer. Okay? Same thing for zoom out. You're going to get 4 times further away. So if you were -10 to 10, zooming in would take you -2.5 to 2.5. Or if you zoomed out, it'd be -40 to 40. Okay, but maybe that doesn't work. Maybe that's not what you want to do. And so there's an option that I really love that we never just seem to talk about. I always, like, this is always something new, which is cool that I get to do it. I like the first one. Check this out. Zoom box. So do it with me. It's that same blinking cursor kind of wherever you left it. So if you weren't messing around with it like I was, it's probably still sitting at the origin. We get to draw the window that we want to zoom into. Okay? And I use my left and right and my up and down arrow keys to get me to a center. And what we're going to try to do is we're going to pick a corner of a box that we want to fit in a certain space. And let's say we wanted to try to fit all of that curvature in the middle. Okay? Do it with me. Let's move our cursor down to kind of this space. I don't know, about 2, -2. Let's say, kind of slide it down to that space. And down here at the bottom, it'll tell you where you are. So there's no guessing whether you're close to 2, -2 or not. All right, so I got to move a little left, too far, a little up, too far, right? And there's that trace step that I showed you. So good. Let's make that our bottom right corner. Here's how we do it. I'm in Zoom box. I'm picking any corner of the box that I want. Bottom right, top left, bottom right. Doesn't matter. Press enter. And look at what happened to your cursor. Now it's a blinking box with an X in it. And what it's waiting for you to do is draw the rest of the box. To do that, watch what happens. Let's go up. Let's take it up to about 1. You can see that when you press enter right there, it started the corner of your box. And now you are drawing that right edge of your box. Okay? Now watch what happens when you slide left to create some 2-dimensional space. So press the left arrow, hold it down, or just press it a bunch of times, and make it look however you want. And wherever you put that cursor, that little box in there, once you press enter, that's what you're zoomed into. Which is kind of nice, that you can pick whatever space you want. Because when we look at sine and we look at crazy polynomials where stuff going all over the place, maybe you just want to look at one certain spot. And Zoom box is a great way to get that picture. Now, that does not mean it's necessarily going to be square. Right? This distance and this distance don't have to be the same now because you picked whatever rectangle size you want. Okay? I love Zoom box. I think it's pretty cool. All right, let's see if we can find this point right there. I want to find whatever that relative minimum is. But it's falling between lattice points. I don't know. It's a -1 point, negative point something and negative point something. I don't know. And you could like try to guess your way to it by pressing a button like trace. All right, because the moment you press trace, now it moves you to the function. So I go from kind of floating around the space, not on it or off it. Trace is going to jump you onto it. And if I press the left arrow to get closer, it's just going to follow the function along. And so I can get pretty darn close. Right? I kind of drew the red circle there. So I have a pretty good sense that it's going to be about right here. But my visualization of this being right and it actually being close are two totally different things. There's a calculator. I want the calculator to do all the work for me. Right? Maybe you've seen this before, but there's a way to find the minimum within a range. Right? To find relative minimum. Okay? And it's actually, let me get rid of that, it's above trace. It's in calc for calculate. So if you press second trace, you might have seen this before, many of us might have. Okay, option number 3, minimum. Okay, so you press number 3, and what's going to happen is it's going to ask us 3 questions. Okay, and the questions are going to be right here. Left bound. In other words, is this blinking cursor to the left of the minimum that you're looking for? Well, no, I tried to put it right on it. So let's slide it over just a little bit. So left, 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 so that it's visually definitely to the left. And once you feel like you're far enough to the left, press enter. And what it should do, in a newer calculator, is going to draw like this almost kind of asymptote looking thing, this dotted line here. If it's an older calculator, it's just going to draw this arrow up at the top to tell you where it's going to look. And you see the arrow's pointing this way because the calculator is going to look this way for a minimum. Okay? But look at the question. Now the question changed. Right bound. In other words, is that blinking cursor now to the right of this minimum? Well, no, I just moved it to the left and nothing's changed yet, so let's slide it to the right. So right, a whole bunch of times until you feel good about it. Doesn't have to be balanced, doesn't have to be perfect, it just has to be to the right, okay? And then I press enter again. And it's gonna draw the other one. And I've got an arrow pointing in so that these arrows are pointing towards each other because it tells the graph, just look in here. Hey, calculator, look for a minimum, a relative minimum in this space right here. And now look at the question. The question is not, hey, do you want me to find exactly the right answer? Or, hey, I'm going to give it to you. Be ready. The calculator is saying, hey, do you want me to guess? Do you want me to give you the best guess that I've got for this? And yeah, the best guess you've got is the best I can do. So I press enter. Okay. And down there at the bottom is the best approximation that this graph has for that minimum point. I have no idea what that is. That's all we need to be able to do. Okay, so I just wanted to give you a chance to see that if you did have to approximate something, and we try not to approximate much here, we try to get nice full answers, even if it's the square root of 2, that's perfect. I don't know what any of those numbers are, right? And with x cubed plus x, and we're trying to find a minimum, it's going to be some square root. And you'll know that once we get to calculus, you drop down the degree, right? We have a degree of 3, so drop it down to 2. There's where your mins or your maxes might be at answers to problems like that, okay? And you can find minima or you can find maxima too. So in calc, if I wanted to find that other point, this one right here, right, that relative max, I do the same thing. I just press maximum in calc instead of minimum. And the question down here at the bottom, they run through the same 3 things, right? Are you far enough left of this point? Well, I'd like to be maybe a little bit closer. So, but maybe I'll slide like towards the origin. Say, hey, start looking here, and I press enter. And now the question is right bound. Okay, let me just move my cursor far enough to the right so I can make sure I can do it. Cool. Enter. Enter. There's its guess. The best version that this calculator can do to find that point is to give me those 2 numbers. Okay, so cool. I love those. The calculator can do a lot of calculating, but I want to. All right. We've got just a couple minutes, so I wanted to kind of preview what we're going to start next week. But I wanted today to kind of be just a little bit of practice, kind of chill. You guys have been working hard, so I appreciate that. I wanted to look at the last part of 1.2, and then we'll be out of here. Okay, so I'm going to go back to here. Relative mins and max, cool, good. Some classes got a chance to talk about step functions and piecewise functions. Some didn't in great depth. That's more of an in-class thing that I want to do. So I'm going to skip that section for now and come back to it. So if I had a chance to talk to you about it and how to graph it in class, cool. If we didn't, make sure you tell me. But we're not going to sketch them by hand. We're definitely not going to sketch them by hand. Here is the end of chapter 1, section 3. So if you could just jot a couple things down in your notebook to start for now, it'll just save us some time when we get back to class Tuesday, Wednesday, and then Thursday, and then we'll see what happens with Friday for next week, okay? But the main idea in talking about the graphs of functions, some things that we look for, because our minds crave it, our brains love symmetry. Love, love, love it. If I look around this room, there's symmetry everywhere, right? Everything's level. The blocks of the concrete are all organized perfectly. My desks are in straight rows. The carpet's got lines on it. It just makes my brain happy when things are symmetric, and that's not a coincidence. That's what our brains are designed to do, to look for symmetry, to look for patterns, okay? And we do that with functions too. And so that's kind of what we're going to start and finish next week. Is we're going to finish 1.3 and wrap it up with symmetry. I think that this is, I don't know, have you seen it before? Have you talked about even functions versus odd functions? Okay, so it's just going to be a recap of stuff that you've seen before. So people just like to sometimes jot stuff down, okay? And really all you have to do visually, I'm going to zoom in, right? When we talk about symmetry, it's all this right here. Okay. If your function is even, its symmetry is to the y-axis. So the y-axis acts as the mirror, right? And it's equal on either side. Okay. If you're symmetric to the origin, we're going to call those odd. But there's another line of symmetry there that people sometimes prefer instead, and it's the line y equals negative x. Right? So you can say it's symmetric to the origin, but saying that it's equal to the line y equals, or symmetric to the line y equals negative x might be visually a little bit easier for you to see that balance. Okay. And then last but not least, what if it's symmetric to the x-axis? Well, it's not a function, so I don't care about that. Right? I want function symmetry, not relation symmetry. So we really only have to worry about functions that are even or odd. We don't have to worry about graphs that are symmetric to the x-axis because those aren't functions. Okay? And here's the key. So this is our last thing, and we'll make sure that we pick this up when we get there. When we talk about even functions, so if a function is even, if you give me some f of x, right? So you give me some function. If I drop in f of negative x, so I change x to negative x. Okay. And I get the exact same y value back, if I get exactly f of x, then it's even. All right, so give me a function, whatever it is, and I change every positive x to a negative one. But I get back the exact same y value, right? I drop in 1 and I get 5. All right, well, if I drop in negative 1 and I also get 5, and I drop in 2 and negative 2 and I get the same answer. I get 3 and negative 3 and I get the same answer, and 10 and negative 10, and pi and negative pi. But I'm not going to test all the numbers. I'm going to test x versus negative x and just make sure that I get exactly what I expect. Then it's even, right? A function is even if given some function. If this is true, then it's even. Okay? And then the last thing, and then away you go. If a function is to be called odd, okay? It's got symmetry in the origin, which is good. But take a look. So you got to be given some f of x, some function. F of x equals, can you see the green okay? Is it green okay? So you give us some function, cool. If I want to test, and that's really kind of up to me, is I actually have to do a test. If I change every x to a negative x, and that's always going to be our test. You probably remember that from last year. So I drop in an x, or regular x, and I get a y. Okay? But if I come down over to the other side and I drop in negative x, it's going to give me the opposite of the y value that I had on the other side, if it's going to be odd. And that's going to be for every single x value. So if I got 1, so I plug in 1 and I get 3. So 1, 3 is a point. Well then, negative 1, negative 3. Right? Plug in the opposite of x, you get the opposite of y. And that's for all of them. In other words, I am going to plug in a negative x, and it's going to give me the negative version of whatever I would have gotten had I just plugged in x. The entire function should change signs. Okay? So that's just a little preview, a little recap of what we'll pick up when we get to class on Tuesday or Wednesday. Obviously, cohort A and cohort B are now flipped in terms of who sees stuff first. So we will adjust as we go, and we'll figure it out from there. Okay, so you might be on slightly different schedules and doing slightly different things when you're in school, but we'll just make it work. Cool? You guys are good. All right, check, now that I know how far we've gotten, I will post some stuff for you to work on just to keep things clear and fresh in your minds in terms of some of the stuff from 1.3. So check Canvas, I would say probably by midday. I'll have just a handful of things for you to work on, nothing too crazy. Okay, short and sweet, quality over quantity. For Tuesday, probably Tuesday night or Wednesday. I'll let you know. Okay, so check Canvas. Thanks, everybody. See ya.
Quick question.
Yes, please. Yay.
With the assignment for that you're going to post midday, Is that for today's work or for like weekend?
For the weekend. Nothing you have to submit by tonight.
Okay.
Absolutely, yeah. So you're here. We went through the lesson. You're good. I will post some stuff that you can work on at your leisure over these next few days.
Okay.
Cool.
Thank you.
You're welcome. Have a good weekend, everybody. Enjoy your Monday off.